For the second unit of thermodynamics, in previous lecture we discussed heat engine, Carnot cycle, work done in Carnot cycle and efficiency of Carnot cycle. In continuation, today we are going to discuss Carnot's theorem, second law of thermodynamics, the concept of entropy and entropy as a state function, units of entropy, the inequality of Clausius and factors affecting entropy. In previous lecture, we showed that the efficiency of Carnot cycle is given by eta equal to Q2 minus Q1 upon Q2, which is equal to T2 minus T1 upon T2. Here Q2 is the amount of heat absorbed from the source and Q1 is the amount of heat liberated to the sink. T2 is the temperature of source and T1 is the temperature of sink. According to this equation, the efficiency of a machine working reversibly between two temperatures depends on the temperature of source and the temperature of sink, and it is independent on the nature of substance or substances used. It can also be said that all periodic machines working between two same temperatures will have the same efficiency, and this statement is also known as Carnot's theorem. You may recall that the first law states that while one form of energy converts to the other form of energy, the energy which disappears is exactly equal to the energy which is produced. But first law of thermodynamics is silent about the extent to which this conversion can take place. Second law of thermodynamics tells us about this point. It says that while all other forms of energy can be completely transformed to heat energy, but heat energy cannot be completely transformed to other forms of energy without leaving some change in the system. This generalization has led to another form of second law of thermodynamics, which states that it is impossible to convert heat into work without compensation. Now we can derive an expression for the entropy through Carnot cycle. The equation which we derived from Carnot cycle, Q2 minus Q1 upon Q2 equal to T2 minus T1 upon T2 can be rearranged as 1 minus Q1 upon Q2 equal to 1 minus T1 upon T2, or we can say that Q1 upon T1 equal to Q2 upon T2. Now this equation may also be written in general form as Q reversible upon T equal to constant. Here Q reversible is the heat exchanged in the reversible process and T is the temperature at which the heat exchange takes place. Now Q reversible upon T is a definite quantity and is known as entropy and represented by S. The equation Q1 upon T1 equal to Q2 upon T2 has been derived by using the positive sign for the heat absorbed and negative sign for the heat released. Therefore, Q2 has been taken to be positive and Q1 has been taken to be negative. If we put both as positive, Q1 and Q2, whether it is heat absorbed or heat released, then this equation Q1 upon T1 equal to Q2 upon T2 will take the form Q2 upon T2 equal to minus Q1 upon T1, or we can say that Q2 upon T2 plus Q1 upon T1 equal to 0. Therefore, it can be said that when reversible isothermal and adiabatic processes takes place in series and in cyclic form, then the summation of all Q upon T terms is equal to 0. Any cyclic process, if carried out reversibly, can be shown to consist of a number of Carnot cycles. Consider a cyclic process in which the change from the state A to state B and back to the state A is carried out reversibly. The path A, B, A may be considered to comprise of a number of Carnot cycles, that is, of a series of isothermals and adiabatics as shown in this figure. The lines slanting horizontally stand for isothermals and those slanting vertically stand for adiabatics of the small Carnot cycles. If each isothermal and adiabatic change is made extremely minute, that is, each Carnot cycle is made extremely small by increasing their number, then the paths inside the loop cancel each another and the cycle corresponds to continuous curve ABA. Thus, any reversible cycle can be considered as made up of a number of Carnot cycles. Knowing that for each Carnot cycle, Q2 upon T2 plus Q1 upon T1 equal to 0, it follows that in the case of the reversible cycle ABA comprising of a series of Carnot cycle, this expression takes the form summation of Q upon T is equal to 0. That is, the sum of all the Q upon T terms of the Carnot cycles is equal to 0. And for an infinite number of Carnot cycles, sigma, that is summation of dq upon T will be equal to 0. Since the cycle is performed in two steps, that is from A to B and back from B to A, it follows that summation of dq upon T equal to 0, which can be shown as integral of dq upon T within the limits A to B plus integral of dq upon T within the limits from B to A is equal to 0. The integral dq by T within the limits A to B is the summation of all dq by T terms when the system changes from A to B along path 1, and the integral of dq by T within the limits B to A is the similar summation when the system returns from state B to the original state A along path 2. From the equation, summation of dq by T equal to integral of dq by T in the limits A to B plus integral of dq by T in the limits B to A equal to 0, we get integral of dq by T in the limits A to B for path 1 will be equal to minus of integral of dq by T in the limits B to A for the path 2, or it can be said that integral of dq by T in the limits A to B for path 1 is equal to dq by T in the limits A to B for path 2. From this equation, it follows that integral of dq by dt in the limits A to B is a definite quantity which is independent of the path followed by the system, but it depends only on the initial and final state of the system. This quantity, therefore, like delta U and delta H, represents the change in some single valued function of the system of state A and state B. This single valued function is known as entropy and is represented by S. If SA is the entropy of the system initially and SB is the final entropy of the system, then delta S, that is change in entropy of the system, will be given by SB minus SA, which will be equal to integral of dq by T within the limits a to b. For each infinitesimally small change, ds will be equal to dq by T, and at constant temperature for a finite change, ds becomes delta S and dq becomes q. Therefore, delta S will be equal to q upon T. As entropy is a state function, therefore, delta S of the states from A to B will remain same whether the process is reversible or not. Mathematically, it will be given by the equation delta S equal to integral of dq by T within the limits A to B only when the changes are brought by reversible cycles. It is because this expression has been derived through Carnot cycle in which all the processes are reversible. It is very difficult to define the absolute value of entropy of a system. Hence, change in entropy is calculated. Entropy change is considered as the sum of all q upon T terms during the whole process. Thus, the entropy change for a finite change of state of a system at constant temperature is given by delta S is equal to q reversible by T. As entropy change is expressed as heat exchanged divided by absolute temperature, hence the unit of entropy are calorie per degree. This is also known as entropy unit represented by EU. The SI unit of entropy will be equal to joule per Kelvin. Entropy is an extensive property. Therefore, the amount involved has to be mentioned. Generally, this amount is taken to be equal to 1 mole. Here, we have an example to calculate the entropy change during vaporization. Calculate the entropy change in the evaporation of 1 mole of water at 100 degrees Celsius. Latent heat of evaporation of water is 9650 calories per mole. Now, entropy change on the evaporation of 1 mole of water is obtained by dividing the latent heat of evaporation of 1 mole of water by the absolute temperature. Hence, delta S will be equal to 9650 divided by 373. Therefore, delta S will be equal to 25.87 calories per Kelvin per mole. Here is another example to calculate the entropy change during melting. Calculate the increase in entropy when 1 gram molecular weight of ice at 0 degrees Celsius melts to form water. Latent heat of fusion of ice is equal to 80 calories per gram. You may note that latent heat is given in per gram and you have to calculate this heat for 1 mole of water. Therefore, multiply this latent heat with molecular mass of water, that is 18. Therefore, Q for 1 mole of ice will be equal to 80 multiplied by 18 calories, and delta S will be equal to Q upon T. T at which ice melts is equal to 0 degrees Celsius, or we can say it is equal to 273 Kelvin. Therefore, delta S will be equal to 80 multiplied by 18 divided by 273, which will be equal to 5.274 calories per Kelvin per mole. Now, let us discuss Clausius inequality. Clausius showed that if in a cycle irreversibility enters at any stage, then the integral of dq by T is always less than 0. The efficiency of irreversible Carnot engine will always be less than the efficiency of reversible Carnot engine. As the efficiency of reversible Carnot engine is equal to Q2 minus Q1 upon Q2, which is also equal to T2 minus T1 upon T2. Therefore, for irreversible process, Q2 minus Q1 upon Q2 will always be less than T2 minus T1 upon T2, where Q2 is the heat absorbed at temperature T2 and Q1 is the heat returned at temperature T1. Therefore, Q2 upon T2 minus Q1 upon T1 will be less than 0. In other words, integral of dq upon dt for an irreversible process is less than 0, or entropy of final state is greater than the entropy of initial state. As most of the processes occurring in nature are irreversible, hence it can be said that during spontaneous process or during irreversible process, entropy of universe tends towards maximum. Now we will discuss the factors affecting entropy. As increase in entropy is considered as increase in disorderness or randomness, hence sign for delta S of system can be given. The first factor which affects entropy is the phase change. When melting takes place, the substance is transferred from an orderly form to a more disordered form. Hence, entropy will increase. Therefore, sign for delta S system will be positive, or we can say that delta S system will be greater than 0. Similarly, during vaporization or sublimation, entropy increases because disorderness or randomness increases during vaporization or sublimation both. As a sample changes from solid to liquid or from liquid to gas, its particles become increasingly less ordered, or we can say more disordered. So, its entropy increases. In this figure, you can see a cube of ice is melting. Here, ice is in ordered form, but this ordered form has been changed to a disordered form on melting. Therefore, entropy is increasing during melting of ice. In this figure, you can see the vaporization of liquid bromine. Liquid bromine is more ordered as compared to vapor bromine. Here, sublimation of iodine is shown. Solid iodine is more ordered as compared to vapor iodine. Hence, during vaporization of bromine or sublimation of iodine, entropy is increasing, or we can say delta S system in both these processes is greater than 0 or positive. Temperature is an important factor to affect entropy. As a sample of the gas is formed, the molecules of the gas become in more random motion. Hence, delta S for this system is greater than 0, or we can say that entropy change is positive. Likewise, as we raise the temperature of a solid, the particles vibrate more vigorously about their mean positions in the crystal, so that at any instant there is a larger average displacement from their mean positions. This results in an increase in entropy, or we can say delta S system is greater than 0. When the volume of a sample of a gas is increased, the molecules can occupy more positions, or we can say that their motion is more random. Hence, entropy increases on increasing the volume of the gas. And conversely, if a gas is compressed, its entropy decreases. Therefore, if volume is increased, the sign of delta S system will be positive, and if volume is decreased, the sign of delta S system will be negative. In this figure, you can see that when a gas enclosed in this bulb is expanded, or we can say the volume is increased for the gas, molecules can occupy more positions, or we can say that these molecules are arranged more randomly. It can also be said that delta S for this change is positive. Mixing of substances without any chemical reaction also affects entropy. The situations in which molecules are more mixed up are more disordered. In this situation, delta S of the system increases. Have a look on this example. Here, two gases are separately enclosed in two different chambers. If this separation is removed, then these two gases will be mixed up. Here you can see that the mixed gases are more disordered than the separated gases, and delta S system will be greater than 0. We know from experience that diffusion is a spontaneous process. We know that increase in entropy during mixing also provides a driving force for solubility of some substances in others. As particles of the solute leave a crystal to go into the solution, they become more disordered. This increase in disorder favors the dissolution of the crystal. For example, when 1 mole of solid sodium chloride dissolves in water, the entropy increases from 72.4 joule per Kelvin per mole to 115.5 joule per Kelvin per mole. Or we can say that delta S for this process is 43.1 joule per Kelvin per mole. Here you can see that in the crystal of sodium chlorides, the cations and anions of Na plus and Cl minus are arranged in perfectly ordered condition. But when this crystal of sodium chloride gets dissolved in water, then disorderness increases, hence entropy increases. When water and propyl alcohol are mixed to form a solution, then you can see disorderness increases, hence entropy increases, or we can say that delta S will be greater than 0 or delta S will be positive for this dissolution also. Increase in number of particles or dissociation of gases or different substances also affects entropy. As in the dissociation of a diatomic gas such as F2 gaseous giving 2F gaseous, any process in which the number of particles increases results in an increase in entropy, that is delta S system will be greater than 0. The processes that result in increase in moles of gaseous substances will have delta S greater than 0. For example, if we take this reaction, liquid hydrazine reacts with hydrogen peroxide to give nitrogen plus water, then you can see that there are no molecules of gaseous substances in reactants, but in products there are 5 moles of gases. As number of gas molecules increases from reactants to products, therefore delta S for this reaction will always be positive, or we can say delta S system will be greater than 0. Now we have an example in which you can arrange the entropies of different substances in order. Rank each group of substances in order of increasing absolute entropy at 25 degrees Celsius and give reasons for your ranking. First group is liquid mercury, solid mercury and gaseous mercury. Now for any substance, entropy increases in the order of solid has less entropy, liquid has greater entropy than solid, and gas has even greater entropy than liquid. So we predict the absolute entropies to increase as solid mercury, which is less than liquid mercury, which is less than gaseous mercury. The second group of substances is C2H6 gaseous, CH4 gaseous and C3H8 gaseous. As entropy increases with molecular complexity, so we predict the absolute entropies to increase in the order CH4 gaseous has the least entropy, C2H6 gaseous has greater entropy, and C3H8 gaseous has the greatest entropy among these three. The third set of substances is calcium sulfide solid and calcium oxide solid. Both of these ions contains 2 plus and 2 minus ions, that is a cation with +2 charge and an anion with -2 charge. Hence, charge alone cannot decide the entropies of these two substances. But O2 minus ion is smaller than S2 minus ion, which shows that O2 minus ion will be strongly attracted towards calcium 2 plus ion. Therefore, it can be said that the entropy of solid calcium oxide will be lesser as compared to the entropy of solid calcium sulfide. In the end, let us revise what we have discussed today. Today we discussed Carnot's theorem, second law of thermodynamics, the concept of entropy and entropy as a state function, units of entropy, the inequality of Clausius, and various factors affecting entropy. In continuation, in next lecture, we will discuss thermodynamic temperature scale and entropy as a function of volume and temperature, and entropy as a function of pressure and temperature.